Hello, good evening, everyone. Yeah, am I audible? So is my,
You are audible. You can check in chat box.
okay. Okay, fine. Today I'm going to, I think already the team has been informed you, I guess. So today I'm going to cover quantum machine learning and the various quantum machine learning optimization algorithms also. So let me share the screen and we'll start discussion. So till like 8, I will be presenting on the concepts. And after that, if any of you are having the questions, you can, we can have a question and answering session after that. And we can discuss on your doubts. Yeah. So I hope screen is visible. So today we are going to cover the concepts on quantum machine learning. So let me present you a quick outline of today's session. So today we're going to discuss on just introduction to the quantum machine learning, and then we'll discuss in detail about the quantum kernel methods, and we'll see how data will be encoded and what are the hybrid pipelines we have in quantum machine learning, and then we'll discuss quantum support vector machine, quantum neural networks, and also variational algorithms along with some applications. If time permits, I'll show you the hands-on implementation also. Otherwise, I'll just show you already have been implemented. That I'll show you like what are the libraries we have to use and how to write the code for quantum support vector machine. So now coming to the introduction to the quantum machine learning, I think many of you are already aware of machine learning. Mostly, I think most of you are already working on machine learning, classical machine learning. So in quantum machine learning, what we are doing is we are combining the concepts of quantum computing along with the machine learning. You can see in this diagram. So, yeah. So as shown in this diagram, so here we are using the machine learning part. This is not fully quantum machine learning concept. Here it is also a combination of classical machine learning approach. So we are not fully doing only the quantum things. We are also adding some quantum machine learning algorithms also to do the post processing and also for the other methods that I'll explain in coming slides. So, first of all, to start working in quantum machine learning, first of all, you need to be clear with the quantum computing principles and also machine learning algorithms. So, if you are good enough in both the cases, then you can understand how to apply quantum computing principles on current machine learning algorithm, so that you can use the advantage of quantum computation or quantum principles in like when you're processing the data using machine learning. Okay, so first of all, what is machine learning with quantum computing? So I'm saying that like if you know, you can combine both, but how these two will be combined? So we are applying quantum principles in machine learning algorithms. Let us say if we talk about support vector machine, we are using that for the feature extraction and also for the pre-processing. We are using by with the classical perspective. We are considering data as binary data, that is 0 and 1. So whatever the data set we are taking, that will be in binary format only. Accordingly, SVM will work operations, and accordingly the data will be pre-processed and feature extraction will be done, right? But in quantum, like if you wanted to develop quantum machine learning algorithms, then you need to convert classical SVM into quantum SVM, where you can apply quantum computing principles, so that the quantum SVM can be so that you can apply or you can do the processing of the information in terms of a processing of the quantum information, right? So here simply like you need to combine quantum principles to the machine learning models to convert it into quantum machine learning. But how to include that? So it is not that easy as we are discussing here. So as I told you, machine learning models or algorithms, whatever we are using now or we are working, are developed based on the binary data. Again, the binary data is different and quantum data is different. So if you could able to convert that into like in terms of quantum perspective, then that will be work that will work on quantum information. So first of all, for the quantum machine learning, the input will be quantum data. So that's why in quantum data, obviously we will be having quantum principles like superposition and entanglement. So accordingly, so whatever the machine learning or quantum machine learning models you are developing, that must satisfy and also should work with the quantum data, which is having the like superposition and entanglement concepts and other quantum principles. So first of all, why the machine learning is important now? Because, like, for example, if we talk about the larger data sets, so as we discussed in the previous sessions, so for example, if I wanted to process one day ChatGPT data, let us say some 1 month ChatGPT data. So obviously, the people, like the users, the worldwide users are using the ChatGPT, so it will generate a lot of data, right, which cannot be possible for a quantum like classical system, or which can be possible but difficult to process by the classical system, right? So to overcome that problem, as a solution to that problem, we need to go to the next technology, that is nothing but the quantum computing you need to add. So when you apply quantum machine learning algorithms on larger data, it will be processed in less time when we compare to the classical machine learning. Because in classical we don't have superposition concept, in quantum we have the superposition. So like when you run or when you try to train and test the data, if the data is also larger, but by applying the superposition concepts, like whenever like we are developing quantum machine learning using quantum principles, so due to the superposition concept, the training and testing time will be reduces, and it works efficiently exponentially faster when we compare to the classical machine learning. And also it will be used to solve the intractable problems. So as I told you, the problems which are difficult to solve using the classical computers, or which are in a complex nature, on that you try to apply the quantum machine learning or quantum computing algorithm, so that you will get the results more efficiently and also in less time compared to the classical machine learning and classical computing also. So this is what quantum machine learning is. But before that, you also need to understand what is the difference between quantum machine learning and classical machine learning, how the data will be processed. So that can be easily explained by this diagram. So this entire diagram is the representation of how classical machine learning process the data and how quantum machine learning process the data. So just consider classical machine learning example. So here I'm just doing pattern recognition. So I've taken some data set which is in classical format. That is nothing but it is in combination of binary data, that is 0 and 1. So I will apply the mathematical algorithms, as I told you, like we can pre-process the data, feature extraction, everything we can done by using the classical machine learning, and then we can run it in a classical processing unit, or if the we can run it in a classical system, or we can also use the GPU for if the data set is too high, like the size of the data set is high. And after running it, we will get the pattern, based on once it is run, we will get one pattern at a time, and it will be recognizing using this particular procedure. So this is for this entire processor, let us say it takes this much of time. Now, the same process, if I wanted to perform using the quantum machine learning, then that can be done in this process. So, first of all, the input for the quantum machine learning must be the quantum data, which is a superposition of state 0 and state 1. So, it is represented in terms of qubit. So, whatever the data set, for example, at present, we are working with the various data sets, right? But all those data sets are represented in classical format, right? But to perform or to apply quantum machine learning, first of all, we need to convert that into quantum data, and on that, we have to apply the quantum machine learning algorithms. So, how to convert classical data into quantum data, and what is the procedure? Even we have the kernel methods to map the data set to the high dimensional space. So, how to convert this kernel methods into quantum kernel, and how to convert the data into quantum data, that we'll discuss in detail in coming slides. But first of all, we need to have a quantum data, and it will be having superposition. And on that, again, we will apply the quantum machine learning model like quantum SVM and quantum neural networks, or like any quantum machine learning models. And then it will be processed in a quantum processing unit. And then after performing the operation, we will get the multiple patterns can be recognized. Like all possible patterns will be recognized using quantum machine learning. But whereas in classical, we can recognize only one pattern based on the like whatever the requirement you have been given to the program. So if you see the time analysis, so here almost 3/4 of time has been taken, and if you see here, it just completed, like if you consider almost 80% of time has been taken for this entire process. Here if you see, it has taken about like 10 to 20% of time. So there is a lot of difference in time analysis. Like it can be used to process the operations in less time when we compare to the classical machine learning, and also we can find out all possible solutions using the quantum machine learning when we compare to the classical. And now we will also see how the processing will be done. So you can concentrate here. So here, let us say we have the data set of 3 bits. Okay, we have 3-bit data set. So when we apply classical, like 3-bit classical data, if we consider in terms of classical, so it is having 3-bit data. On that, we will apply the quantum machine learning models, and then finally we will get the outcome. Right, from using 3 bits, there will be total 2 power 3 possible combinations. So after applying the machine learning model, we can get any of the, like based on the algorithm whatever we have written, accordingly we will get the outcome as any one of the combinations, right? But when you apply the quantum machine learning on the same data, so the process must be like, so first of all, you need to convert this classical data of 3 bits into quantum data. Okay, so when you convert it into quantum data, you will apply superposition, right? So in that case, all possible combinations, like 3 bits will be converted into 2 power 3 possible combinations. That is, you can see here 8 possible combinations. So whenever it has been converted, it will be in this way. Okay, it is a superposition where it can be represented in all possible combinations. And on that quantum data, we will apply the quantum machine learning algorithms. And after applying the quantum machine learning algorithms, we will find the patterns, all possible patterns, and from that, whatever the required outcome we have, that we can take and that we can transmit to the classical data. So this is how a quantum machine learning will be processed, and the difference between the classical machine learning and quantum machine learning. So these are the various applications that also we'll discuss in detail in coming slides. But like I mean, we are applying machine learning on various applications, right? Similarly, in on same applications, you can also apply the quantum machine learning. But only thing is, you need to be aware of how to, like you need to be aware of encoding operations to convert classical data into quantum data, and you need to be clear with the quantum kernel. Okay. So this is how machine learning, the differences between the classical and quantum machine learning is. Now we'll see how quantum, we are saying that quantum will enhance the machine learning operations, but how it enhances means, first of all, the speed up of the operations will be increases. So it is exponentially faster compared to the classical due to the superposition, because we are converting data into quantum, so superposition will be added. So automatically it will be exponentially faster, right? And even if the data sets are larger, like if you wanted to apply it on large data sets or computations, then quantum machine learning will outperforms the classical machine learning. And also even here we are encoding the data in terms of quantum, so again it will generate the quantum states by adding the superposition. That also gives uh, all possible outcomes in a single run. And also the optimization will be enhanced, because if we take complex models, its global minima will be faster compared to the classical application or classical machine learning. And also we can solve the complex problems which are difficult to solve by the classical computers. Even with the supercomputers, we can apply. I think if you are aware of yesterday, I think, yeah, yesterday Google has been announced, I think today morning we got the news. So Google has been announced that they have been done one verifiable experiment. So with that, it has been proven that, like a quantum computer 13,000 times faster than the world's best supercomputer. So they have done the same experiment on supercomputer and also the quantum computer. So it has been proven that it is 13,000 times faster than that. So this is how it is actually working, and it is even in real time also it is working. So it is not only in mathematical perspective or just some basic implementation or the implementation perspective, but it is coming to the real time. So soon you can also see the quantum computers in most of the places. So once it is done, we can see the very good results and what we are seeing today. But at the same time, it also increases the challenges for the classical computation. Okay, and also in case if you wanted to handle the big data, then quantum machine learning is one of the best solution to handle that. And because here we have the parallelism concept that will be due to the superposition. So this is how a quantum will be used for enhancing the machine learning models. And these are some examples, but apart from that, quantum machine learning has advantages in almost all the domains. Like if you apply it in chemistry, or if you apply it in, like how we are applying machine learning in various domains, so if you apply it in any of the domain, obviously it has been proven, like it has been proven that it will outperform the classical model. But only thing is you need to have the large data. If you apply it on smaller data set, as I told you in previous sessions also, if the data set size is too small, and if you apply classical and quantum, you may not see much difference, because on smaller data sets, even classical will works better, right? So you try to compare the results on larger data sets, where even classical computer will feel some difficulty in computation, or feel some difficulty in processing.
ఇంటికి తీసుకొని తెస్తానులే డబ్బా శ్రీ మనిషి
Hello, any doubts? Okay, this is hello, someone unmuted the mic. Please mute yourself.
Ma'am, from your end only that.
No. Disturbance is coming, no? Some
Yeah,
disturbance.
from your end only it's getting noise.
One is here, sir. I'm getting from some other side, I think. Okay, now is it fine now?
Okay, now you can try, ma'am. Can you unmute yours?
Okay. Am I audible now?
Yes, ma'am.
Yeah. Okay, so these are the existing quantum machine learning algorithms which we can use for processing the data. So even as we have the classical neural networks, we also have the quantum neural networks. So even we have the quantum support vector machine, even quantum principal component analysis, and also VQA. We'll see how each and every algorithm works like in detail. Okay. So now, first of all, before going indeed, like before going to discuss about quantum machine learning models, first of all, we need to we need to understand quantum kernel methods. So as I told you, even in like I think most of you are already aware of kernel methods. What is the use of it in classical machine learning? So to map the data to the high dimensional space, we need to have a kernel method. So already we are using that in classical machine learning, but here in quantum machine learning, the data is quantum data. So to map that quantum data, here we are not mapping it to high dimensional space. We are mapping that to Hilbert space. Because as I told you, if you wanted to work on quantum data, first of all, it has to be in Hilbert space, and also it need to maintain the coherence, right? So first of all, whatever the data set you have, or whatever the data you have been given, that need to be mapped to the quantum Hilbert space, right? So for that we have the quantum kernel methods. So there is a slight difference between the classical kernel and quantum kernel. So you can see here, so this is mathematical representation for the quantum kernel. So, one second. So this quantum kernel is used to point the quantum data to the Hilbert space, as I told you. So it will be used to map the data to the high dimensional Hilbert space. So for that, we have the mathematical equation. You can see this. So here we are performing the inner product. So in quantum, like even yesterday when we were discussing, I used the terms like inner product, outer product, and also the fidelity. So here, first of all, to perform the inner products, sorry. So when we talk about classical kernel methods, we have normal tensor operations and also normal multiplications. So there we don't have the concept called inner product like quantum data and all. But here, to convert the data into or to map the data to the Hilbert space, you need to perform the inner product on the data. So first of all, what is this inner product and how the calculation will be done on inner product? Let us say Qx and Qi here we have been represented, but let us say we have the state 0 and state 1. So this mathematical is representation is very much important in machine learning, because you will see inner products and outer products in various algorithms. Okay. So in inner product, what we'll do is the product will be done between states, two different states, let us say state 0 and 1, and these two are represented in this way. Okay. So here if you see, this 1 is represented in correct Ket notation, but this 0 is represented in reverse direction. So that's why whenever you will do the mathematical calculation, you need to do the reverse order. In this sense, you need to do the transpose of that particular vector. So 0 will be represented as what? So we already know the vector representation for each quantum state. So 0 is represented as 1 and 0, and 1 is represented as 0 and 1 in vector, right? So as this is a reverse representation of a Ket notation, you need to do the like transpose operation. Okay, when you do the transpose, rows will be converted into columns and columns will be converted into rows. So it will become 1 0. Okay, and it will is 1 will be as it is. Now you have to do the multiplication between these two. After doing the multiplication, what you'll get? 1 into 0 will be 0 and plus 0. So it is equals to 0. So the calculation of, even to calculate the probability, fidelity, we will use the inner product, but there it is different. Okay, that I'll explain whenever we'll discuss about the fidelity. But this is how inner product will be, operation will be performed. So in inner product, the product between two states will be done in this direction. So like even apart from inner product, we also have the operation called outer product. So where we have the states, let us say state 0 and state 1. Here state 1 is represented in reverse Ket notation, because here you need to apply tensor operation on, transpose operation on state 1. So 0 will be represented as 1 and 0, and now 1 will be represented as 0 and 1 with transpose operation. So you need to do the transpose. So now again it will be converted 1 and 0, it will be, and it will be converted into 0 and 1. Now again do the multiplication. So after doing the multiplication, what you'll get here? 1 into 0 will be 0, and 1, 0 and 0. So here the dimensions will increases. When you do the outer product, the all possible dimensions will be represented, all possible combinations will be represented. And when you do the inner product, its probability will be calculated. Okay, so this is how the data will be mapped to the high dimensional Hilbert space. So this equation will be used for the quantum kernel as a quantum kernel. So first of all, we will take the input. On that input, this kernel method will be applied, and after applying this, the data will be mapped to the Hilbert space. But before that, the classical data, whatever we are taking, need to be converted into quantum data. So for that, we will use the encoding operations. So like how the encoding will be done, that I'll explain. But this is what about the quantum kernel. So in quantum kernel, we will perform the tensor operation between two different states, or maybe between the same state. So based on the data. So this is the difference between the classical kernel and quantum kernel. So this is a representation of classical kernel. So in classical kernel, let us say we have the data points x and y. So after applying the kernel model, it will be mapped to the high dimensional Hilbert space. High dimensional space. Okay, classical high dimensional space. But when you see the quantum kernel, so when you apply quantum kernel methods on the data, this will be a quantum data. So it will be mapped to the high dimensional Hilbert space. It's not a only high dimensional space, but here the space is represented as Hilbert space, where the coherence will be connected along with these qubits, and it has to maintain the qubit until performs the operation. But once it lost the coherence, means the data will be lost. So that's why again there are challenges in quantum machine learning. So first of all, encoding the data into quantum is a challenge, and then mapping that to the Hilbert space will be again one more challenge, and also making it to be in coherent state. Then that also, like it again, when we discussed in last class, I already told you the photon particles are in fragile nature, right? So even this maintaining coherence and all, when we run it in real quantum system, again we can face the challenges over there. But anyhow, we have the advantages. It is we can even come across the challenges also. Already people have been started implement, implementing error correction and noise mitigation techniques, you can apply those for maintaining the coherence and also for getting the better accuracy. Okay. And now we'll see in detail how this quantum kernel method works. So here, first of all, we have the data space. So it is like any data set we can take in a classical representation. So when we talk about classical kernel, the data will be converted into high dimensional space, and this is by using the classical kernel module. And when we talk about the quantum kernel, so first of all, the data need to be converted into quantum data. So that conversion will be done using the unitary matrix. So you need to apply unitary matrix on each data point to convert it into quantum data. So once it is converted into quantum data, you have to apply the quantum kernel methods to map it to the Hilbert space. So this is the difference. Here the data will be represented, the data points, whatever we have been taken, that will be represented on feature space, and on that classical kernel will be applied. But here the data need to be first of all converted to the quantum features, like quantum data, and then it will be shown on the feature space, and on that quantum kernel will be applied. Quantum kernel methods will be applied to make like map it to the Hilbert space. So this is how the process will be. And now we will see what are the different quantum kernels we have. So as I told you, like, I mean, there are various kernel methods. We can, the one is quantum feature map kernel. So where in previous example, I've been represented, right? Here the feature map is like we have been converted and we have been mapped the data from this in Hilbert space. So that kernel method, we will call it as a feature map kernel. So here the same method in a product we will be using. And first of all, before applying kernel method, first of all, you need to convert the, or you need to encode the data. So that data, classical data will be converted into quantum data by applying unitary matrix. And then you will apply the kernel method. So which we have been discussed in earlier example. Okay. And mainly it will be used in SVMs, so to support the classification, and it has various applications in like chemical structure classifications or drug designs, genetical, like even now people are working on gene classification, right? So on those, this feature map kernel will be very helpful. And apart from that, we also have fidelity based quantum kernel. So in this, so till now, like here we have been consider the data and we have been directly mapped that, but here we will consider the fidelity. So fidelity is nothing but, first of all, so actually here the performance of or the outcome of any quantum circuit will be calculated in terms of fidelity. Let us say, for example, we have a graph. Okay, so I have been applied. Let us say I've been taken input as 0, and on that I have been applied Qiskit. So what could be the output? Obviously, we know that it is 1 because it will gives the I mean complement of the input. So let us say after running it in real quantum system, I got, let us say, so after applying, okay. Okay, so let us say the input I have been taken is 1 and the output I got is 0. And here, this is the representation of state 0 and this is the representation of state 1. So as per the input, I know that if I give the input as 1 and after applying Qiskit, I get output as 0 with 100% probability. But when you run it in the system, let us say the 98% or 98% or let us say 0.98, because we are calculating in terms of probability. So the probability is 0.98 and here 0.02%, or you got output as 1 with the 0.02% like probability. So what does it mean? Mathematically, we know that whenever we apply NOT gate on any input, the output is complement of it. So it can be proven mathematically also. But here the problem is when you run it in real quantum system, due to the internal noise, here the value is different. So in that case, we will compare these two results. Like for example, how near it is to the real outcome. Let us say the real outcome is what, 100%. That is, it must be 1. But here we got it is 0.98. So we can say it as 98% fidelity. That means it is 98% near to the actual outcome. So this is how fidelity will be calculated. And even based on that fidelity, also we can develop the quantum kernel. So for that, we have this equation. So this equation is used to calculate the fidelity of any of the state. If we talk about whatever the circuit you are developing, that circuit fidelity can be calculated in this way. So Px is the, as I told you, so the actual fidelity, let us say Py is the actual fidelity as per the mathematical modeling. or Px is the fidelity which we got after running it on the system. So the comparison of this two will give the actual fidelity, or it can also be represented as efficiency of that particular circuit. If the fidelity is high, then automatically your algorithm is working good, and it will be useful to apply in various applications like that. So the justification you can give based on the fidelity. So these fidelities can be used for developing the quantum kernels using this equation. But as I told you, that concept is little. I mean, as you can see, the concept is little complex, calculating fidelity, and again fidelity depends on many internal things, because how it is running in quantum system, and how photon particles are reacting, everything will be dependent, right? Everything will affect the fidelity, so that's why it is little difficult and also little complex to develop the kernels using this method. But we also have this model. If any application is required such kind of model, then we can use this fidelity based quantum kernels. So usually we can use it for the mixed states. For example, if you wanted to combine noisy hardwares, like if the hardware is really noisy, and if there is no much difference, or there is no much problem with the fidelity or the noise levels, in such cases you can use fidelity based one. And also, like for medical applications, if we talk about any healthcare applications and all that, in that also you can use the fidelity based quantum kernel. But in most of the cases, the people use the feature map kernels because of I mean, because of the less complexity when we compare to the fidelity based one, and also it is easy to prove mathematically also. So this is about the various quantum kernels. And this is circuit representation for the quantum kernel. So there are two methods for developing the quantum kernel, and also we can, as I told you, we will perform inner product, right? So here, if we talk about the feature map, we need to perform the inner product. So to perform the inner product, there will be two different architectures. So one is by using echo test. So this is the first one, where these two operations will be used to perform the inner product. And the second one is swap test, where we'll use the swap gate to perform the inner product. So any of this circuit we can use for developing the, like when you are developing quantum machine learning models. So to apply the, or to convert, or to map the quantum data to the Hilbert space, then you can apply any, or you can develop any of the circuits, and you can use that as a kernel method, and based on that the data will be mapped to the Hilbert space. So here simply we are using the Hadamard gates and unitary gates. So even unitary gates is required to do the inner products. So here along with the unitary gates, we are also using the Hadamard gate. And here swapping will be done to swap the data to the higher dimensional Hilbert space. Okay. And this is how the process will be done. So how the data will be, like raw data will be mapped in Hilbert space or in high dimensional space. If we talk about the classical data, let us say we have the raw data, which is a combination of multiple parameters. And if we talk about the classical kernel methods, then first of all, this will be encoded. The data will be the data with various parameters will be encoded by using the classical encoding methods, and then it will be mapped to the high dimensional Hilbert space. And then like first of all, data must be on feature space, right? And then like we can apply classical kernel methods to map it to the high dimensional Hilbert space. And if we talk about the quantum machine learning, then same data set will be encoded by using quantum encoding circuit. So usually we'll use unitary gates for encoding the classical data into quantum data, and then that will be mapped to the high dimensional Hilbert space by using the quantum machine learning quantum kernel models. So this is how, after that, we can apply the quantum machine learning algorithms on that particular data, which has been mapped on the Hilbert space. So this is how a process will be done in classical and quantum, like the difference between classical and quantum machine learning models. And now we'll see, sorry. Now we'll see how the data will be encoded. So as I told you, like whenever we wanted to apply even to apply quantum kernel, first of all, we need to encode the data, right? So to encode the data, there are various encoding techniques. So the first one is like to encode it into feature maps. First of all, like the first one we have is the basic encoding. So simply whatever the binary data you have, directly you can represent that in terms of quantum state. So if we talk about the binary, T vector binary, it is like 101, then it is equivalent to the binary as the quantum state 101. Directly with get notation you can represent, and it is one of the simplest way and also the direct way for mapping the data to the high dimensional Hilbert space. And the second method is amplitude encoding. So where the encoding will be done based on the amplitude. So here amplitudes are nothing but like we have the what we say, like yesterday I've shown you the probability graphs and all, right? So in that the amplitudes will be represented. So those amplitudes will be used for encoding the data, and with that we can map the data to the high dimensional Hilbert space. And these, but the problem here is what we say, like the amplitude to prepare the amplitude based encoding, usually it is associated with high cost. So it is so if you are okay with the high cost, then you can even try with the amplitude encoding. And next we have this angle or rotation encoding. So where the feature maps will be rotated, like the data will be mapped in Hilbert space by rotating the data in terms of various rotation gates. So as I told you yesterday, the rotation we have seen, right, in composer we have the rotation gates rx, ry, rz. So any of the rotation gate you can use for rotating the data and encoding that into quantum inform, like encoding classical data into quantum by rotating that along with either x-axis, y-axis, or z-axis. So if you see like encoding operations, few may use rx gate and few may use ry gate. So it completely depends, like if the measurement is according to z-axis, then accordingly they may use Rx gate or Ry gate. If the measurement is according to Y gate, then accordingly, like the rotations will be done. Okay. But here, the major advantage with the rotation gate is it is hardware friendly, because in quantum, we have the rotation gates, and most of the circuits or most of the quantum machine learning models would use the rotation encoding for mapping the data to the Hilbert space. And we also have the hybrid fusion maps where we can combine multiple, like we can combine basic encoding, amplitude encoding, or multiple encoding strategies. So often these will be used in the variational quantum circuits. So we'll see what are those. But here the limitations of basic encoding are, like if the data is high dimensional, then it is difficult because we are directly representing. So it is just three dimensional, so we have been represented. But if the data is having some lacks of uh, uh, lacks of inputs or lacks of parameters, then it will be difficult. Okay, and even amplitude encoding also will gives the good result, but it is of little high cost when we compare to other. Okay, so we are going to discuss quantum support vector machine in coming slides. So in that also we have been discussed, I mean, we have been developed or we have been applied encoding techniques. I mean, nothing but rotation encoding technique we have been used there. So this is about the data encoding and various encoding techniques we have. And then we also have the hybrid pipeline. So as I told you, I mean, as we have the representation, so these hybrid pipelines are used to combine a quantum and classical processing. So as I told you, a quantum machine learning is not fully a quantum operation. So here it is a combination of quantum and classical operations. So usually this data encoding, everything will be done, and we will measure the outcome, and then to optimize it or to post process it, we need to apply again classical models. So for that, we need to combine classical and quantum circuits. So for that, we will use the, I mean, hybrid pipelines will be used. So usually in VQAs and the QNNs, in what are the quantum algorithms we have, in all the algorithms, hybrid pipelines will be used, because all these algorithms are the combination of classical processing and also the quantum circuits. So without this pipelining, it is difficult to get the data, or it is difficult to optimize or measure the data in. Okay, so if you see usually hybrid pipeline will be represented in this way. We will be having the classical logic data, and it will be containing some parameters, and then we will apply the quantum processing techniques. We will convert it into quantum data, and we will also apply the kernel methods, and we will do the quantum processing. But again, once the processing has been done and once it is measured, to optimize it or to I mean, to optimize it or to do the post processing, we need to apply again classical logic. Okay. So this is how a quantum and classical will be combined together to perform the quantum machine learning operations. Okay. So after performing post processing with the classical method only, we will get the result. So this is how hybrid pipelines will be helpful. So now we'll see in detail about the quantum support vector machine. Am I going fast? If so, just let me know so that I'll just slow down the pace.
No, ma'am, no.
Okay. So now quantum support vector emission we'll discuss about, but how like a support vector emission will works, like how quantum QSVM works, we will see. So first of all, quantum support vector machine is used similarly in classical. We have the SVMs, right, for pre-processing or for classification purpose. We're using all those in the classical machine learning. Similarly, in quantum also we will use the quantum SVMs. So here we have, as I told you, we need to apply the kernel methods, right? So to apply the kernel method, you need to do the inner product. So for that, here I've taken the example of 4-bit data, 4-bit quantum data. I've considered data set as 4-bit data. So on that, to perform the inner product, we have seen, no, like QX and QY, the state QX and QY, and on that we have been performed the inner product. So here also we'll perform the inner product. So for that we have the we need to use the unitary gate and unitary dagger. So where we will apply the transpose of that. And these are the rotational gates. As I told you, first of all, the data need to be converted into a quantum data, and then we will apply the rotational gates. So these rotational gates are used to, used to maintain the coherence in a quantum Hilbert space, and also will be used to, correlate the data. Okay, and after that we will apply the entanglement. So what is the need of entanglement and why we are discussing about the entanglement is that I'll explain in quantum neural networks. But this is how quantum support vector machine algorithm works. And first of all, the data will be taken. It can be any of the data set. Okay, so that will be converted into quantum data by applying unitary methods, and then we will apply the quantum kernel models or quantum kernel algorithm to map to map a quantum data to the Hilbert space. Okay, and then we will do the simulation. Here you can see, even when we like this entire process is for the quantum kernel. So once it has been developed, then we have to do the simulation. Either if you wanted to run it in real quantum system, you can also run it in real quantum system. So there we again have the noise simulation and noiseless simulation. So when we run it in real quantum system, it will be associated with the noise. The internal photons will be having the noise, and you can also work on the simulators where there won't be any noise associated with. So there you can check. So whether your algorithm is working good or not, that you can check with the simulators. If you get the good result in the simulator with the very minimal noise which has been manually added, then if you are confident with the results, then I suggest you to go and run it in a real quantum system. Otherwise, unnecessarily you have to pay the amount for, because now none of the quantum system is of free of use. So you have to purchase the runtime and then you have to run your models. So as it is a quantum machine learning, obviously takes a lot of time for running. So in that case, the cost for that will be increases. So I suggest you to work with the simulators first. So once you get the confidence on your algorithm, whatever you have been developed, and if it is working good and giving the good accuracy, then you can go and run in real quantum system. Okay, so this is how, and once it is done, like processing is done, to get the final outcome, like we will apply the machine learning, we will be like tuning will be done in hyperparameter tuning, we will be doing hyperparameter tuning also for these things. So this is how quantum support vector machine will be developed and will be used for performing the operations. Okay, so now let us say I would like to explain you one example. Okay, so let us say we have some two data points. So if I wanted to map that to the feature space, then how to develop the okay, so just let me explain one after the other step. So here, let us say even you have the same, like this task will be useful. So just try to understand the concept. So here I'm saying that SVM will be used to map the data.
Ma'am,
Yeah.
I have a doubt regarding QSVM.
Okay.
Uh, where I have been used to implement one simple problem statement which I have been given to my students, which has been
Mhm.
working with the SVM, and then we have worked with the QSVM. With the two
Okay.
qubit we have used, but we work with the simulator. We have not tried any of the hardware. But
Okay.
in one case, it has been given the better accuracy, QSVM. But in some case, in another case, QSVM is showing lesser accuracy than the classical algorithms. Is that possible
What?
or
No, no, it is
sorry?
possible, ma'am. So what may, yeah, it is possible. May I know what is the data set size?
The data set what we have been used was the lesser, like not so big data set, because we have been used with some depression analysis data set, which has been available in audio as well as the text. We have used around 1,000 lines of text data and followed by audio. For text, it was giving a lesser accuracy. For audio, it was giving a better accuracy.
So here the problem, ma'am. So in text, like we cannot, when you map it to the quantum states, it will be like 1,000. I mean, 1,000 samples will be very very less. But when we
Yeah.
convert audio into the data, then it will be the size little bit increases. But here the
Okay.
what I suggest you is if you wanted to see the difference between classical and quantum, I suggest you to work with the larger data sets because as I told you, if it is a smaller data set, then we have many classical machine learning algorithms which will work
Yeah.
better. But even
Okay.
like as I told you, like a simple example, let me tell you. So for example, we have the addition of two numbers program. Okay, so if I run it on classical system and if I run it on quantum system, then automatically classical will work better. Quantum, if we
Yes.
are using that for the quantum, it is actually useless first of all, right? So
Yeah.
same here, yeah, same here. For initial case, if you wanted to experiment with quantum SVM, you can try with the smaller data sets, but there you cannot see the difference between classical and quantum, and sometimes classical will work better, as you said, like as you
Yeah.
experienced.
Yeah.
So what I
Yeah.
suggest is go with the larger data sets. So then you
Okay.
can see the time analysis. There will be difference in time analysis. Obviously, if you see the training and testing time in classical and quantum, there will be huge
Okay.
difference. And at the same time, you can also see the difference in accuracy also.
No,
So
the thing
once try
is,
with,
yeah, the thing is, when we are taking the large, I mean, huge data set, it was taking too much of time while we are encoding classical data into the quantum.
yeah, that problem we have,
Uh,
and that challenge we have.
yeah, that's why.
I
That's why
suggest you
we have
to use.
chosen the.
True,
Sorry.
ma'am, but try to use GPUs, ma'am,
Okay.
for that. It will be
Conversion.
fast
Okay.
because yeah, because as you
Okay.
said, that is one of the challenge that I'm going to discuss in
Uh,
coming slides. Because we have the advantages with the quantum machine learning, but at the same time, in current scenario, we have a lot of challenges also. Like we don't
yeah,
have
yeah,
the
yeah.
hardware availability at present, and even quantum required the highest computational power. Like even the systems need to have a high computational power, so otherwise it will take a lot of time.
Okay.
So that's why, like I suggest you to like even I'm suggesting the participants to work on simulator. If you run same
Yeah.
thing on real quantum system, no, then cost will increases like anything because
No, we
the
tried with the
cost.
simulator because it is with respect to the student's perspective. No, I was just trying with the simulators. We have not been worked with the hardware of any of the quantum stuffs.
Okay, so
Yeah.
no problem. I mean, you just once a try with the larger data set, you can see the difference then. So now
Okay.
with the
Okay.
smaller data set, that fluctuation will be there. As I told you, when you run the same algorithm multiple number of times, there is a fluctuation in accuracy also. Sometimes you may get 92 and sometimes you may get 93 or it may be reduces. So it is due
Yeah.
to the internal noise. So even in simulator also some little bit noise has been introduced manually. But yeah,
Okay.
but when you run it in real quantum system, you can see the huge difference also because again it works on photon particle, right? So we can't
Yeah.
say how it reacts to the operations.
And
But
the other,
I
yeah.
yeah, ma'am, tell me.
And the other thing, if we increase the number of qubits, is the accuracy affects in any way?
No, it will not affect, but it will take a lot of time for encoding the data.
Yeah, that's true.
So if you associate, like if you include GPU for, I mean, if you use the GPU, then you can see, I mean, it will be little better. But if you run it on normal system and all normal processing unit, no, then it will take a lot of time.
Okay. Okay.
Hello,
Better
ma'am.
option is GPU for encoding, which you are suggesting to us.
Correct, correct.
Okay.
Hello,
Thank
ma'am.
you. Thank you.
Yeah. Hi, ma'am.
Ma'am, what I noticed is, so classical machine learning algorithm gives more accuracy for text data, and quantum computing gives more accuracy for audio data. Why? Because we know that we must convert this quantum states into qubits, right? So the process, we know that that is encoding. So for doing this encoding, this is highly discrete, because there we are going to use words letters, right? So that, according to my idea, text data gives, if we are going to use text data in classical machine learning, it will give more accuracy.
No, no, no. I mean,
So
actually, yeah, that's not
quantum,
correct. No, no, ma'am.
that's not correct. No?
Yeah, for
Okay.
even for the text data, quantum will give the better results than the classical, but only with respect to the data set size. If the size is high, then automatically you can see the difference. So even when we talk about the text data, usually the size of the text data will be less, right?
Okay.
So in such cases, like even we worked with some text data set. I don't remember exactly the name of that. It is having some large, like the size of that is large, a little bit larger. So when I ran it in classical and quantum, I could able to see the result difference. Like quantum has been given better results than the classical. So there we got almost the accuracy of some 80. So that was little complex data set. So
Mhm.
80 around I got for the classical, and in quantum I got around 87. So difference we can see, but only with respect to the data set.
Yeah,
So
yeah, this is I have been observed, ma'am. QSVM I have used for other data set where it was giving a for text data better accuracy. Only with respect to some data set, I told no that depression analysis data set where I got the
correct,
lesser accuracy. That's why I was in the
correct.
dilemma why it has been less here. Thank you.
No, no, that happens, ma'am, because as I told you, it depends on the data, what kind of data it is there in the data set. Again, the size of the data set. So many things will affect the quantum machine learning model. So if in case you are getting less accuracy than the classical, don't worry. Try to increase the data set size and just check it out how the data has been represented, what are the various parameters you have. If the complexity is more of, or if internally it has been not in that level, then you may not get the expected results in quantum. Like you may not see the difference between the classical and quantum. Usually in such cases, like classical will work better, but even I suggest you to try with the various data sets, like various problems, and for the various problems we will be having a lot of data sets already available. So try to run the quantum machine learning models on various data sets and just check it out, because even for the text data sets also it has been given good results. In some cases it has been not given as good as classical. So both the cases are there, but again, as I told you, depends on the data and also the size of the data sets. Okay.
Thank
So
you.
just let me explain. Yeah. Okay. So just let me explain you about how quantum SVM will be used to map the data, or like how it will be mapped and what is the feature map circuit we have. So I just considered two data points. It is very small circuit, but I just wanted to explain you because most of you are having difficulty or maybe having confusion how data will be mapped to the feature map, like to the Hilbert space, and how quantum SVM will be working. So for that, you can concentrate on this circuit. So if I wanted to like apply quantum SVM on two data points, let us say some 0, 1 and 1, 0 randomly have been taken. So for that, first of all, you need to apply the you need to use the rotation gates, like it can be RX gate or RY gate. As I told you, few people or in few models they have been used RX gate and RY gate. So RY is nothing but we are rotating the qubits along y axis. So in between this, you need to add the C0 gate. So here we need to add C0. This is nothing but C0 gate representation, which we discussed in previous classes. So you need to add C0 gate for developing the entanglement. So what is the need of entanglement here is, so when we talk about the classical machine learning, there must be a correlation between the data points, right? So in quantum, we cannot directly say that these will be correlated. So we have to apply a gate or apply an operation which develop the correlation between the multiple qubits. So here C0 will be used like that. So with this, it will be generated as an entanglement, and these entanglement will be used to maintain the correlation between various qubits. So this is how QSVM circuit will be developed to represent the feature map and also to represent the like correlation between multiple qubits. So this is for the example of 2 qubits. So similarly, you can also apply for the 3 qubit, but there the representation of C0 gate will changes. So that I'll explain in QNN, quantum neural network, in coming slides. So this you can explain in like the operations of this can be explained in this way. So first of all, we will apply the unitary gate, and then we will apply the rotation through the y-axis gate, and on that we will perform the tensor operation. So here the C0 gate is nothing but performing the tensor operation, right? So this will make the entanglement. So this works like an entangler which will maintain the correlation between the multiple qubits. So once it is done, then the data can be mapped to the feature space, and then you can apply any quantum machine learning models. So this is how SVM will be working on 2-qubit system. If you apply 3-qubit, then one more qubit will be added here, Q2, and accordingly you need to increase the number of gates. So here these two will be same, and one more rotation gate you have to add, but this entanglement need to be modified. So in entanglement also we have 3 different types of entanglements, so that I'll explain in coming slide. So now even quantum in like as I told you, even if I wanted to apply QSVM, even I need to use the quantum kernels, but it supports various quantum kernels. So even it supports the linear kernel, so which we have been seen in previous example. So rotation gate along with the C0 gate, that will be used as a linear kernel, and we can also use the polynomial kernel. So where the rotation will be done through the RY axis, and also we will use the additional parameters, like we can also use the additional coefficients. So all this will be calculated with the angles which a quantum state will be making with the other axis, right? But apart from that, we can also take other coefficients, or we can also give some polynomial data, and based on that we can also map the information. And also we can use the fidelity kernel, as we discussed in earlier example. We can use the fidelities and for mapping the data to the Hilbert space, and also we can use the entanglement enhanced kernel. So where a fidelity, like we will use the fidelity, like it is like continuation of fidelity kernel. So if we apply entanglement to the fidelity kernel, then it will be converted into entanglement enhanced kernel. So where we can use the Hadamard gates and also the C0 gates along with the superposition operation along with the fidelity. So this is used, and it is little bit complex when we talk about the other kernel representations. And we also have the variational quantum kernel. So where we will use the rotation along z-axis for rotating the data and mapping it to the Hilbert space. So these are the different kernels which QSVM supports. But in most of the cases, we'll use the linear kernel, which is one of the simplest method and also easy to develop. Okay, so this is about the various kernel methods that supports QSVM. And now we'll see the applications. So as I told you, QSVM, like as we have the applications of classical SVM in many domains, similarly we also have the applications of quantum SVM in various domains. The first thing is, if you talk about any diagnosis or any health issues, like if you talk about the prostate cancer, so it has been recently proved. So only have been included which have been proved with the experiments. But apart from this, we can also apply QSVM in various applications. Okay, so recently experiment has been done on prostate cancer detection, and it has been proven that QSVM has outperformed than the classical SVM, and it has been given very good results than that. And also can be used in financial risk assessment. Even yesterday one ma'am has asked about the fraud detection. She's working on fraud detection, so even we can apply QSVM on fraud detection, but only like you need to concentrate on the data set size and the parameters of the particular data set. And we can also apply it for credit scoring if you wanted to like detect the complex patterns of the users. Like when we talk about the credit card details or any the transaction details, then usually the transaction history will be huge, and it will be little bit complex. In such applications also you can apply the quantum SVM. And also to detect the fraud, like even any anomalous or any fraudulent things happen, or any fraudulent patterns if you wanted to detect, then you can apply quantum SVM on that also. And even we can apply it in medical diagnosis. So it has very good applications in I mean, it has a lot of advantages in healthcare sector, quantum machine learning. But at the same time, it is at present we need to also concentrate on the challenges which we are going through. So if you could able to reduce those challenges or internal disadvantages of a quantum system, then it will give like even the better results what we are seeing today. But even it has been proven that in medical diagnosis also QSVM is giving good results. So one one example is prostate cancer detection, which has been proven, and also it can be used in breast cancer classification. So with the huge data set size, it has been outperformed the classical SVM. And also we have the applications of QSVM in cybersecurity. So even if anomaly detection or any spam detection or any intrusion detection or any malware, if you wanted to detect, in such cases also you can use the quantum SVM for the accurate results than the classical machine learning models. So these are some examples of the quantum SVM. But apart from this, you can apply it on any of the domain on which we are applying classical machine learning models today. Okay, but still, like as I told you, there are some problems, like when we run the same algorithm when we run the same algorithm multiple number of times, there is inconsistency in the result. Like sometimes we may not get the same result. For example, if you talk about the classical program, if I have written any classical program, if we run that for the multiple number of times also, I'll get the same output, right? But in quantum, it is not like that. So due to the internal, if the noise levels changes whenever that particular algorithm interacts with the photon, if it interacts in a different way, or if it generates more noise, or if the gate noise increases, then all this will affect the overall accuracy of the model. So that's why there will be little bit fluctuation in the outcome. And but at the same time, like we have the advantage, but at the same time we need to concentrate on all these things. So to overcome such kind of things, we can apply the noise mitigation techniques and also error correction mechanisms along with the machine learning models, quantum machine learning models. So there you can see the better results than the quantum machine learning models without any noise mitigation techniques. So this is about SVM in detail. Now we'll see quantum neural networks. So for the quantum neural networks, we have the base of classical neural networks only. So it is not, even when we apply quantum neural networks, it is again the combination of quantum models and also the classical models. So here we have been converted, like we have been applying neural networks, like we are applying this on quantum data. So you can see here. So usually quantum neural networks are developed by applying the quantum computing principles like superposition and entanglement. So usually they have been taken base as a classical neural network, but they have been converted that by applying the quantum principles like superposition and entanglement. And then they are saying it as a quantum neural network models. Because if I wanted to apply neural networks on quantum data, it must support the quantum information, right? So for that, we need to convert classical neural networks into quantum by applying the quantum principles. And then, for that, first of all, quantum neuron will be calculated by using the unitary matrix, as I told you. So first of all, quantum data. First of all, even to apply the quantum neural networks, also we need to have a quantum information. So for that, first of all, you need to convert classical data into quantum data by applying unitary matrix or unitary gate, we can say. So once it is done, it will be activated and it will be considered as a quantum neuron. And then you can apply the parameterized gates. So like you can apply the rotation gates or CNOT gate for the entanglement, as we have seen for the quantum SVM. So in a similar way, you can apply for the quantum neural networks. And this is the example for the quantum neural network, how the data will be processed. So here, first of all, data will be taken and that will be processed by using the rotational gates. So we can use the RX gate or RY gate. And after that, you have to use the entanglement. So this is the entanglement, right? So what is the need of entanglement here is, as I told you, it is used to maintain the correlation between the quantum bits or quantum states. So even in the entanglement also, we have the different entanglements. So for example, if you don't have this a C naught, let us say if you have these two, then this combination is called as a linear entanglement, or linear entanglement, where we have the entanglement between the uh, like the what we say, entanglement between the multiple qubits in a order. Like for example, first we will maintain the develop the entanglement between first two qubit, and then entanglement will be generated between the second and third. So this is in a successive process, like our successive way. So this will be represented as linear. So if you see this, let us say we will consider this one. So this will represent the circular entanglement. So where you are generating the entanglement between qubit 1 to 2, again 2 to 3, again 3 to 1. So it is in a circular way. So that's why this entanglement is called as circular entanglement. And there is also one more entanglement where you have these two, and also you will generate one more entanglement between the qubit 1 and qubit 2. So there will be entanglement between all successive qubits. So this is called as a full entanglement. So when you are converting the data, or when you wanted to process the data in quantum machine learning, first of all, you need to apply the entanglement to maintain the correlation. In entanglement, again, we have the three types. Either you can be having a linear entanglement, or circular entanglement, or full entanglement. Okay. So now, even in classical neural networks, we have the hidden layers, right? So we will generate the hidden layers, and based on that, we will process the data. Similarly, in quantum neural networks also, we will be having the hidden layers. All those hidden layers will be represented with the rotational gates and also the entanglement. Okay, so you can develop any number of hidden layers like this. For example, this is one hidden layer. If you wanted to apply one more hidden layer, then same block you can copy and you can paste after this. And after that, you can have a measurement. So before measurement only, you have to do all these things. So you can apply the same. Then I mean, you can apply any number of hidden layers on the data to check the like the accuracy of the model, and then you need to measure the data. Once you measure, then you need to apply the like the data will be represented in terms of vectors, and then you need to apply the optimizer. So here post processing will be done by using the classical models. So that's why this is completely I mean, this is a combination of a quantum models and also the classical data. Okay, so this is how a quantum neural network will work. So we'll be having the data input, and then we will process the data by using the hidden layers. So you can apply either one hidden layer or two or three hidden layers according to your requirement. Or you can even check like based on how many number of hidden layers you are getting the good results or better accuracy. Okay, so this is the example for the three qubit representation, and previous have been shown on 2 qubit. So you can also apply it on 4 qubit. So even on 4 qubit also entanglement will be generated in a similar way. So you can apply entanglement between 1 and 2, 2 and 3, and 3 and 4. This is for the linear entanglement. And if you wanted to apply circular entanglement, then this will be 4 to 1. And also you can apply the full entanglement, where the entanglement will be represented between the successive qubits. Okay. So again, as I told you, based on the model or based on the operation, for few operations, linear entanglement may work good, and for some operations, circular may work good. So accordingly, you need to check. Like I mean, you need to apply the various models, and you need to check which is working good on your data. Okay. So now, even in like even in quantum machine learning, sorry, quantum neural networks, you need to develop the parameterized quantum circuit. So this we will call so that so before that, I just wanted to explain what is parameterized quantum circuit. So as I told you, there will be multiple layers of like multiple hidden layers which are developed by using the rotation and also the entanglement. So this combination we will call it as a parameterized quantum circuit. So usually all this will be trained and tested by using the classical optimizers we have, right? Adam optimizer and SPSC. So all this, like you can use the same optimizers, but those will be applied on the quantum data. So that's why it is not fully quantum machine learning now. It is a combination of quantum and classical models. So even we will use the cost function to calculate the expectations value. So even the cost function is calculated in this way. So again, here also we are performing the inner product. So where we are applying the state. So it can be the state 1 or state 0 based on the outcome, and will be performed inner product along with the angles, like the angle it is making with the other axis. Okay. So this is how a quantum neural networks looks like. So we will be having the data that will be pre-processed by using quantum support vector machine, and then we will develop the internal or hidden layers. So we will call hidden layers means, as I told you, there will be a combination of rotational gates along with the CNOT gate, which generates entanglement. So you can use any number of hidden layers. So that we will call it as a parameterized quantum circuit. So you can use any number of circuits which represent the hidden layers, and based on, and then you can apply the classical models for even. So once the hidden layers are applied, you will measure the data, and then you can apply the quantum optimizers to get the final outcome. So this is how a quantum neural network will work along with the classical models. So now we'll see the advantage of quantum neural networks. So as you know, like we have the advantage of quantum neural networks in almost in all the domains. But only the thing is, like we need to concentrate on current NASQ era, because there will be large noise levels that we need to concentrate on. But it can be used in high dimensional data. For example, if you have a large data, a large amount of data, then you can apply quantum neural networks. And also it will be suitable, like even because we're using multiple hidden layers, any number of hidden layers we can use. So it can also be supports noise data. Okay. And now if you see the applications, it can be applied in various domains.
ఇట్లా అదే డౌట్ వచ్చింది ఇంతమంది అడిగినది అందరికి అదే వచ్చింది వెళ్ళటం అని చెప్తుంది అందరికి
May I know from where we are getting the disturbance? Okay. Yeah, so now we'll see the applications of quantum neural networks. So we can apply quantum neural networks on quantum chemistry applications. So as I told you, if you wanted to develop the molecule, like in quantum chemistry, we will be having multiple molecules, and the combination of that will give the new chemical. Yeah, hello. Yeah, new design. So in that case also we can apply the quantum neural networks. Actually the lot of work sorry actually the lot of work is going on in quantum chemistry. So it is actually showing the advantage, and even the researchers are getting very good results using the quantum machine learning. And we can also apply on finance, like for portfolio optimization and for the risk analysis, and even if you wanted to do the stock prediction. In such cases also you can use the quantum machine learning, and obviously it has the applications in healthcare and also in cyber security, like to detect the anomalies and all. And also will be used in the operations or the applications where the data set is too large and is difficult to handle by the classical machine learning. So in all such cases you can use the quantum neural networks and quantum machine learning models. But what are the
What is the NISQ devices?
hello?
What is the NISQ devices using hybrid pipelines? What the advantage in quantum computing?
NASQ device means like at present, whatever the quantum system we are using, it is an NASQ era, ma'am. So NASQ is nothing but noise intermediate scale quantum era. So all this, like whatever the quantum systems we have, all this comes under this era. Okay, this is not the name of any quantum system, but it is the current era of quantum computation or quantum hardware. Okay, so by default, noise will be associated in those quantum systems, and we can at present, like whatever the methods we have been discussed, those can be used for processing the data. Okay, so the first thing is we have the hardware limitations, and the second thing is we have the plateaus. So where we have, if we have the gradients, right? Cost functions, all this we are using here. So if the circuit design is too complex, then we will be getting. I mean, in most of the cases, few operations of those circuits will be vanished. So this is happening internally due to the internal noise. So that is also one of the challenge at present. And one more thing is scalability. So if as I told you, like if the circuit is having more number of qubits, then automatically it increases the error rates. For example, as previously ma'am discussed, if we use more number of qubits, then automatically complexity increases. It takes more time for converting the data into quantum, and also to map it on Hilbert space. And also we have the encoding overhead. So even as I told you, there are various encoding techniques. So even few encoding techniques works good, but those are expensive. If we talk about the amplitude based encoding, it gives good result actually, but it is expensive. So these are all the key challenges we have at present. The major challenges with the hardware limitations, like due to the internal noise, we have a lot of limitations, and due to that, it will generate the, or it will reduces the overall accuracy. So this is about the quantum neural networks, and now we'll see the variational quantum eigensolver. So these are all the optimization algorithms. So this eigensolver is used in various optimization techniques. So usually you can you can see here. So actually why it is designed is to maintain the if we talk about like if we talk about any molecule design or any chemical based what do we say experiments, so we need to have a ground state energy. So in such cases, if you have this lowest eigen values, then it will give the better results. So it also will be represented by using the Hamiltonian. So in VQE, first of all, the data will be mapped to the Hamiltonian, and then it will be, yeah, hello. Yeah, then it will be calculated by using the again inner product, and those will be used in various applications. So even this is one of the part of quantum machine learning. Most of the like quantum chemistry, if people are working on quantum chemistry or quantum materials or optimization problems, already we are using VQE in that. So this maps the data to the maps the data to the ground state energy by using the Hamiltonian operations. So usually the process will be done is first of all in this Hamiltonian decomposition will be done, and then we will prepare the data in quantum representation where we will apply the unitary operation. So we will call it as Anstas preparation, and then we will apply the like again the kernel methods will be applied. Sorry, quantum machine learning models will be applied by performing rotation and C0 operations. Okay, then we will measure the data using the quantum measurement, and then energy evaluations will be done. And finally, the optimization will be done by using the classical optimizers. So this process will be continued until we'll complete the complete processing until we'll complete the entire process. Okay. So now the applications of VQE are like, as I told you, it has applications in chemistry. Like if you wanted to develop any chemical reactions. One second. One second. Okay, sorry. Yeah, so it has applications in molecular design. So we can have in chemical like in the development of chemical reactions and various applications of chemistry and all, we can use the VQE. And also to develop the spin models, as I told you, we have the various qubit representation, spin qubits and all. So if you wanted to develop any spin models and Heisenberg models, you can use the VQE for that. And also if you wanted to develop any combinational problems where you need to map the data using the Hamiltonians, in such cases also this can be useful. So this is about the VQE, but usually VQE will be having applications in almost all the domains. Even in optimization also we can use that. But usually QA/OA will be one of the efficient algorithm to apply it on optimization algorithms. So this VQE is mostly used for the molecular designs and where we need to have a ground state energy. So now coming to the quantum approximate optimization algorithm. So like even the name itself is saying that approximate optimization algorithm. So it has the applications in optimization problems. Like if you talk about like logistic optimization, or if any domain where we need to do the optimization, then we can apply the QA/OA algorithm. So it will be calculated usually. I mean, yeah. So it will be like, as I told you, in VQE, we are using the Hamiltonians, right? Here also we'll use the Hamiltonians, but that will be prepared by using the quantum states. We will take the, let us say if the state, quantum state is psi, and it is a mix of multiple representations. For example, if we talk about the state 0 and state 1, or the different phases, then it is a mix of all those things. So that will be represented using the Hamiltonians. So using this, usually it will be developed. So when you apply it on real applications or any of the, when you run it on real data set, you could able to see exactly how it is working. So now people are working on optimizing the like when we are optimizing the routes or traveling. If you talk about traveling salesman problem, if you wanted to optimize the route, then we can apply the QA/OA, and it has given very good results compared to classical optimization algorithms. And the process here is, first of all, we need to have a cost Hamiltonian, same like the previously what we have done. And then we will also apply the mixer Hamiltonian, where we will combine multiple phases or multiple states of a quantum system. And then we will initiate the states by applying the superposition, because we need to convert that into quantum. So superposition will be applied. And then we will calculate the depth. So here a quantum circuit depth is also one of the important measurement to calculate the accuracy. And then finally optimization will be done by applying the inner product. So this is how like QAOA algorithm will work, and then we will apply the classical optimizers to to map the data to the to convert the data into the required results. And now these are like the applications of QA/OER. Like as I told you, it has applications in almost all optimization problems. You can use it in max cut problem or graph coloring or portfolio optimization or logistic optimization or routing or scheduling. So wherever you require the optimization, there you can apply the QA/OA. Actually, it is giving very good results. Like now, a lot of research is going on with QA/OA algorithm. People are applying that on various optimization algorithm, like optimization problems. So even like it is one of the one of the efficient algorithm in current scenario, which is giving very good results on optimization problems. Okay, so actually I thought of showing hands-on on Qiskit platform, but as I told you, I've been updating my Qiskit platform to 2.2, right? But when I try to run the, because already I've been developed this in Qiskit platform, but this updated version is not supporting the quantum machine learning functions. Like we have some quantum machine learning functions, those are not supported. So that's why I just explaining what have been implemented earlier. Okay, using the Qiskit platform only, the same platform which I explained yesterday, to explain about the noise aware circuit design, right? And also, like we have also discussed entanglement representation in Qiskit platform. In the same platform, I've been implemented this. You can see here. So here we have taken Matplotlib library and NumPy. These are all we are using for the machine learning, also classical machine learning also. And here I'm using the backend as AER. As I told you, this AER will be supported for the few versions of Qiskit, and for new version, it is not like this backend is not supported. So now again, we are using the circuits. So here, as I told you, we need to map it to the Hilbert space by using the rotational gates, right? So even we need to apply it to the feature map. So for that, we have the ZZ feature map, which will be imported from the Qiskit circuits. And we also need the Aqua models. So these Aqua models are also supported in older version, but not in the newer version. Okay, and we also have the quantum SVM, which is already has been implemented. And then we can use the data sets. Like if you wanted to use any existing data sets, or if you wanted to map to any new data sets, those are also you can represent here. So we have the seed. So here you can represent the samples. So here I've taken 10599 samples, and those have been initiated here. And then we need to we need to map it to the feature space, right? So for that, I'm just applying this ZZ feature map, and where I've been considered the dimensions, we already have some feature dimensions, the functions which are we have already. And for the entanglement purpose, I'm using the linear entanglement. So as I explained earlier, so whenever you wanted to map it to the feature space, you need to apply the rotations. So those will be those will be covered using this function. And even to apply the entanglement or to apply the C0 gate, you need to select either it is linear, circular, or full entanglement. So you can even try with the different entanglements, and you can see how the result you are getting. And then I'm just applying, developing the equation for the QSVM, and that I'm storing in the variable QSVM. So here it will be having the feature map, which we have been already mapped the data to Hilbert space here. And we have the training input and testing input and data points. So these are training and testing inputs we will be giving from the data set. Okay. And then we also need to initialize the what we say, like simulator. So in IBM, we have a chasm simulator that you need to initialize as a backend. And then you also need to, initialize the instance, like how many number of shots you wanted to run and what is the seed and all. So here backend, we have been taken as chasm simulator. And number of shots I'm representing here is 1024. It is same like epochs in in machine learning, right? And even seed. So seed initially we have been taken 10,500 change samples that we can represent here, and even you need to represent the transpiler also here. And finally, I'm running it on quantum, like this quantum instance. I'm just running it on backend with this representation. So after running this, you will get the the instance will be generated, and then you can even see the testing and testing accuracy also. So for that, you have to write these representations. Even here also, you can increase the numbers. Like even when you're counting, you can increase the success rate with the different counts. Sorry, yeah. So here one I'm printing here is test ratio, and second one I'm printing is prediction from the data points, and also like all these predictions, and we are just completely mapping the data to the feature spaces, and from that we are getting the outcome, and finally we are calculating the success rate with the equation, because here it is in terms of the percentage, so that's why we are multiplying it with 100, and for that we have the equation to calculate the success rate. Okay, and then the matrix, like whatever the kernel we are applying, that we have been represented here. So this is how a quantum SVM will be developed for a small data set. Let us say I've been taken only 10,000 sample, so that is smaller data set only. So for that, like this is the process you have to use. But as I told you, in this few functions will not be supporting the newer version of the Qiskit. So this have been developed on the older version. So this I've been applied on the like image processing data set. So where I got the image, but as I told you, as the data set size is just small, 10,000 only. So here I didn't get much difference between the quantum and classical. I got a little bit better results than the classical, but not in a not a huge difference. Okay, so actually I thought of showing that also, but unfortunately that Qiskit not even supporting any of this. Even it is not supporting this features map, and also it is not supporting Aqua, because mine is new. So for the people who are using Qiskit 1.0 version, 1.2 sorry, Qiskit 2.1 version, it will be support, like it will support them. So I just updated 3 days back only to 2.2. So that's why like these functions are not supported by that. So this is how you can develop or you can write a program for quantum support vector machine. Okay. So now we see the applications of quantum machine learning. So as I told you, there are various applications, where we can apply quantum machine learning. So you can apply it on drug discovery, or you can apply it on healthcare, security, even to design the molecules like in chemistry, like a chemistry research. And you can also apply it on optimization problems, and also you can apply it on agriculture. So if you talk about I think most of you are already aware of Quantum Valley, which has been which has been announced by the AP government. So in AP government, their first target is to concentrate on agriculture. They are trying to apply quantum machine learning on crops, to improve the crop yield. So that research, that was their first target. So if they could able to get the good results on agriculture, then they are trying to, they are planning to extend that to the various other domains. Okay. So this is about various applications of the quantum machine learning. Even apart from this, you can also concentrate on even the other applications. So the wherever you're applying machine learning today, on the same applications, you can also apply the quantum machine learning. But only thing is, if you wanted to get like the accuracy, or the accuracy depends on the data set size, and also like even like as I told you, like you have the quantum SVM, the data is available, the code is available, but if you could able to modify that based on your data, like whatever the data set you're using and on what data you wanted to apply, if you could able to do the modifications at model level, then you'll get the better results than what you're like using the existing one. Okay, so even for neural networks also, if you do the modifications at model level, if you use the multiple hidden layers, and if you could able to modify the representation, and also if you use the different entanglement representations, like either circular, linear, or a full entanglement, even accordingly the results may also vary. So that's why I suggest you to just go through, try to do the modifications at model level, uh, not just by simply using the existing and applying that on various data set may not give the good results, or may not, like, because most of the people will work on that. So if you do it model level, then automatically novelty will be added to your work. You may see the even better results. And now coming to the challenges and limitations. So as we discussed, there are many challenges and limitations we have in current research, like in quantum research. The first challenge is with the internal noise. So that internal noise again leads to the errors. So for example, if you talk about noise or even the decoherence. So even yesterday I just explained what is the decoherence is. So qubit must stay in Hilbert space. It has to maintain the coherence in Hilbert space. But if it comes out of this Hilbert space, then whatever the data we've been stored will be lost, right? So if any of this case, if decoherence occurs or if any internal noise increases, then automatically that affects the error. So we need to have the error detection and correction mechanism. If we could able to apply that with the machine learning, we can see the very good results or the higher accuracy than what we are seeing today. And one more challenge is the coherence time. So as I told you, qubit can live for the very short time. So if you could able to increase the coherence time or lifetime of a qubit, then automatically the I mean, we can perform the operations on that for a longer time, and even we can perform the various operations on a single qubit, because it will be live for the longer time. Then automatically we can see the better results than like the qubits with the less coherence time. So this coherence time again depends on the materials. So which quantum material you are using to develop the qubit. So that again leads to the coherence time increase, like increase in coherence time or decrease in coherence time. And then to do the quantum machine learning research, for example, if we are simulating on the data, so that is fine. But if you wanted to run it on real quantum system, or if you run it on if you wanted to apply it on various applications, for few applications we require a specialized hardware. And also the quantum hardware, like whenever we are running it on real quantum system, again it depends on the hardware, like how it has been developed and how it will be interacting with the various operations. So at present we need I mean, this hardware also associated with the high cost. So this is also one more challenge. And one more challenge is data preparation. So as I told you, we need the quantum data as an input for the quantum machine learning. So we need to convert classical data into quantum data. We are saying that we have the kernel models and we also have the quantum machine learning models. But it is not that simple what we are saying in words, right? When we apply directly, if the data is huge, then converting that into quantum will be a complex task. So that is also one of the challenge now. And also algorithmic complexity. So as I told you, even if we have seen only 3 qubit representation using the rotation and CNOT gates, but when we wanted to apply this on some 100 qubits, let us say we have the huge data where we need 100 qubits, then automatically the complexity of the algorithm will increases, right? So even it will be difficult for us to check how the algorithm is working, and also to design the algorithm. And if any problem occurs, or if you are unable to get the expected outcome, then it is also difficult to trace the algorithm where it is doing wrong or where you have done mistake. And also the major challenge, one more challenge, is skill gap. So there are a lot of opportunities outside, but the thing is the people who are skilled in quantum computation are less at present. So that's why even slowly, when we compare to 2023 or before that, now the people who are started working in quantum has been increased, but still it is not sufficient for current research requirements. So we need more skilled students. Like even if we talk about the students, we need more skilled students who are good in at least quantum basics, and even the faculty who can train the students in quantum computation. So this is about the challenges. Now, if you see the future directions, so there are various future directions where you can look into. So it is not only related to the machine learning, you can also concentrate on error correction. So if you wanted to develop the good hardware, like quantum hardware, or like even as I told you yesterday, so we can't imagine a quantum system without error correction mechanism. So even you can work on the scalable error correction mechanisms, which can will be used with the quantum hardware, and which can advance the quantum hardware also in terms of processing the operations. And then You can also concentrate on developing new algorithms. If you talk about machine learning models, you can also concentrate on new machine learning models. Because as I told you, whatever the machine learning models we are developing or whatever the quantum models we are developing, all those have been taken a base as a base from the classical machine learning and classical computation. Those have been converted based on the quantum principles, right? So if you could able to work on that, and if you could able to develop your own architecture or own algorithm which can be converted based on the quantum principles, then that will be a novel work. Even if any of you are interested in doing the PhD, you can also concentrate on this developing new protocols or new algorithms. And also you can concentrate on hybrid models where you can integrate classical and quantum computations. So it not only for the machine learning, you can also concentrate on security perspective. You can combine classical and quantum computation or cryptography for the betterment of security. And then also you can concentrate on various applications like climate modeling, robotics, because now not much work is happening in these areas because these are little bit difficult or little bit complex. When you add quantum to this, it will again increases the complexity. So that's why research is going on, but not in expected level. So you can even concentrate on this, even autonomous systems. I think recently I've seen job notification by the Rolls Royce. So they have been given notification for the quantum researchers. They wanted to recruit the quantum researchers for their autonomous vehicle. They just wanted to convert it into, like, they wanted to apply quantum to their autonomous vehicles. So even there are a lot of opportunities are started in various domains. Even you can think of all those things. Okay. And also you can concentrate on standardization and frameworks, like you can even work on some patentings, and even you can work on combining classic like academia and also industry oriented any applications. Okay, so so these are few future directions, but apart from that, as I told you, quantum can be applicable on any domain. So you can apply that to any of the application and try to check how it is working. So yeah, that's all about today's session on quantum machine learning and variational algorithms. So if you have any doubts, you can ask me. We can have a question and answering session now.
Excuse me, madam. This is Lakshmikant Reddy. May I know what are the main differences between classical machine learning and the quantum machine learning? Uh, there will be some main differences. So, according to large, if the data set is large, then most people say some accuracy rate is uh, good among the classical machine learning, and some people say it is in quantum. So, provided in the classical machine learning, the accuracy rate will be more only if the data set is large. But apart from that, what will be the main differences between classical machine learning and quantum machine learning, madam?
So, like as I told you in today's session, sir, there is first of all differences with the data. The data must be in classical, and here it is like quantum. So the data itself is increases the complexity. First of all, you need to, because we have the data sets and all the input data we have in classical perspective, that you need to like convert it into quantum. So there you will be having a huge challenge, because if the data, if you're working on 2 or 3 qubits, then it is easy to understand how that has been happening. But when you apply it on larger data sets with the larger number of qubits, then automatically complexity increases. So that is one of the challenge where you the major difference. And apart from that, as you said, the data set size also matters when we talk about classical and quantum. So if the data set size is less, then automatically, like, I mean, in most of the cases, classical will outperform the quantum. You will get the better results using the classical. But when you see the larger data sets, again, it depends on the parameters, what you're using, and how you're applying the model. So here, that's why I was telling to work at model level. For example, the data set size is larger,
Okay, madam.
you have been applied
Okay,
classical
madam.
and quantum machine learning, but in that case you got less accuracy in quantum machine learning, because that model, whatever the existing algorithm, QSVM and all, may not be effectively working on those parameters. So if you could able to understand what parameters are there, and if you could able to modify it model level, then automatically you can see the better results. But anyhow, if the data set size is high, then quantum will outperform the classical. But by considering that, like the data, like parameters, what have been represented in the data set, and how those are reacting with the various operations.
Okay, madam. Madam, how much will be the size of these 1 qubit? If we want to measure 1 qubit is, it will be measured in like megabytes or kilobytes, or how what is the 1 qubit is equal to how much, madam?
So qubit is equals to, like, we will not measure in terms of bytes or something. Like we will measure it in like, as I told you, like the qubit is, or like the quantum state is represented in what we say, like a
Qubit.
microwave signal. Yeah, microwave signal, right? It
Okay.
is a signal representation. So frequencies and all we will represent. So the frequency of qubit is so and so. But usually that will not we will not use in computation perspective. But when you
Okay.
work at qubit level, then we will see what is the frequency and what is the amplitude of that particular qubit. So it is not bytes or bits, it is amplitudes and frequencies of that particular the particular signal. Because we are simply saying that qubit, but when you wanted to perform the operation, that qubit will be converted into microwave signal. On that, we will apply the gates and we will apply the operations. So
Yeah,
it will be
madam.
in terms of frequencies. Yeah.
Okay, madam. Madam, I think this quantum computing is more suitable to people, faculty, or whatever may be. I feel, my feeling is that it is quite suitable to triple E and ECE branches rather than
No,
CSE and.
no, no, not correct, sir. Actually, it is very useful for the CSE also. Like we have lot many applications, but only thing is we need to know the characteristics of qubits. So even if it is electronics, electrical, or computer science, or any of the department, if I wanted to
Okay.
work with the qubits or quantum system, I need to know what exactly the system is. For example, let us say classical computer. Okay, so now we have the computer. We are not developing the computer as a computer student. We are having the already properly developed the system, which have been done
Okay.
by the electronics and electrical and mechanical and various departments, and we are using the, like, we are just developing the algorithms and the softwares, and we are just running our programs. But without that system, it is difficult to work for us. So even as a computer science student, even I need to know what exactly happening inside the system. For example, I'm writing an algorithm based on the data, like based on my input data. For example, if I give so and so data, I should get so and so output. So for that, by thinking how the classical hardware has been designed, accordingly, I need to write the algorithm, right? Similarly,
Yeah.
in quantum computer also, we need to understand first of all what is quantum computer, because it is not same as a classical. It is completely different. So once you
Okay.
understand what is a quantum computer, then any person can use that. So again, when you are trying to understand quantum computer, then you need to learn about quantum mechanics, quantum physics, and all this electronics. Everything will come into existence. Even as a
Okay.
classical system is a combination of transistors and electron, like power and all, no? So there also we need to understand, but already we are aware of classical system, so we are not getting difficulty in understanding all those things, because here quantum is new to us, so we are thinking in that perspective. But it is as
Okay.
like equally useful for any of the domain people.
Okay, madam. Thank you, madam.
Okay, sir. So any other doubts?
Yeah, good evening, madam. This is Dr. Oblish.
Yeah, good evening, sir.
Madam, for example, if you want to write an article, research article, we need to write some contribution, new contribution, right?
Correct.
So, for example, any breast cancer detection by using QSVM, of course, you written some article. Now, what is the new contribution in this? Means that contribution point of view, what are the new things what we can implement?
So
In any
new things we can implement is, like, already QSVM has been implemented, but as I told
that's
you, if you work at model level, like for example, QSVM, as I told you, like we will be using rotational gates and also CNOT gates, right? If you could able to modify instead of rotational through Y axis, if you could able to use RX gate or RZ gates, just check it out how that model is working. If that is working good on your data set, then automatically that is novel thing now. So you need to work at model level for the novelty purpose.
what
Otherwise, you
changing
can.
of gates. Changing of gates is one of the new things, right?
Yeah, and changing of the gates means you cannot give like any of the gates. You need to do the rotation operation because we need to convert that into quantum. So rotation need to be done. But again, depends on through which axis you are rotating the information. Accordingly, also outcome changes. So I just try to like I'm ask even if we talk about the entanglement, you can also apply linear entanglement or full entanglement or circular entanglement. So you try to experiment with different entanglements and different rotational gates, and then just see how it is working. If you could able to find the better results with the other rotations and other entanglement methods, then automatically you can come up with the new solution saying that for so and so data set, this model of QSVM is working good than the any other thing. So that will be novel work which has been developed by you. So you can even go for the publications. Apart from that, you can also apply the existing QSVM on the various data sets because the people are still working on in this area. So there are a lot of data sets and a lot of problems are available which are not even started in quantum machine learning. You can look into those problems where there is a lot of research scope and a lot of requirement in current, like if you talk about societal requirement, then on that also you can work, sir. Like if you get any new, I mean, better results than the classical, with that also you can go for the publication.
Okay, thank you, ma'am. Ma'am, can you share this material, others notebooks?
Yeah,
I'll
sir.
be
Actually, even yesterday also you asked. I'll just check it out, sir. Once I'll just check it
yes,
out
at
and I'll
least
just
we should practice at least as a basic letters.
correct. But anyhow, the video will be shared in the LMS, no? Like even you can go through the video, but I'll just check it out the possibility to share the material.
A notebook, that's whatever
Hello,
you
ma'am.
design. Just
Yeah, sure, sir. That notebook even yesterday also asked. I'll just download and share it with you.
thank you.
Yeah.
Hello,
Yeah, ma'am.
ma'am.
Someone asked. Yeah, hi, ma'am.
Ma'am, for hybrid or cloud quantum execution, what are the requirements recommended for configuration, ma'am? Anyhow, we know that minimum requirements, if we are going to work with this hybrid or cloud quantum execution, what are the requirements you are going to recommend configurations? Major
So
requirements to
have
execute this QML algorithms.
correct. So if, it again depends on the application. If you're working on the security or any optimization problems, the normal
Okay.
laptops or normal process will be sufficient. But when you work with the yeah, but when you work with the machine learning, quantum machine learning, huh?
Lot of concepts are there.
Somebody is
Okay, sir,
disturbing.
కూర్చుంటాడు
Yes,
కదా
ma'am.
అయిపోతుందని రోజు ఒక కాన్సెప్ట్ చదివితే
Okay. So when you work on quantum machine learning, you need high performance computers, like even not high means like not even like if you have the processor, like if it works with the i11 processor, i9 processor or i11 processor also you can work with. But only thing is if the data set size is too high, then it requires a lot of time to train and test the data. In such cases, I suggest you to use the GPUs. But apart from that, normal
Oh,
laptops will be sufficient to do the experiments on cloud quantum.
ma'am, in the GPU, any specific GPU we need to use? Any specific GPUs are there?
No, like if I mean, there's no
NVIDIA
specific GPU.
RTX like
Yeah, usually NVIDIA
mm,
will be suggested, but most of the colleges will be having GPU, no? So that will be sufficient. Rather than the
oh,
company or the thing, that will be useful. But yeah, so for quantum machine learning only, I'm just suggesting. For other operations, normal laptop is sufficient with the processing speed.
mm. Yes, ma'am. Yes, ma'am.
Oh,
Okay. Thank you, ma'am.
Ma'am, I have a doubt.
okay. Yeah, sir.
Actually, for quantum neural networks, we choose the phase itself as the weights, right? There are no separate weights.
Correct, huh? Yes.
Then what would be the initial choice of the weights, and will the existing traditional algorithms like gradient descent work for them as well as
No,
they do
no.
for classical algorithms?
No, no. Gradient descent you cannot apply for the quantum neural networks because, as I told you, the input for the quantum neural networks will be quantum data. So that will be developed for the classical perspective. So you need to, so these weights will be like we will be having the cost function here. So before, like even to calculate the weights and all, we will be using cost function, which has been developed by using the inner products. So again, those inner products will be applied on quantum states, like when you are converting classical data or when you are encoding classical data into quantum data. So now you will be having the quantum as an input. On that, you need to apply the inner products so that you can apply neural network operations. So these will be different, like even that will be represented as weight, but even the gradient descent and all will not be directly applied on quantum data. You need to modify according to the quantum information.
Okay, so the result of the cross product will be chosen as the weight vector for quantum, right?
Yeah, so cross product, I mean the inner product, we can call it as inner product and
Yeah,
cross
yeah, I know.
product are
Yeah.
different. Yeah, yeah,
Okay.
different again. So inner product will do.
Okay, so it is optimized. Those values are already optimized before they are used for the neural network, right?
Correct, correct. So because as I
Okay.
told you, like whatever the circuit you develop, that will be optimized before running it in quantum system. So that's why we are using the transpilers and all. So we need to optimize, and then like automatically that will be done. And then on optimized data, operations will be performed.
Okay, thank you.
Ma'am, I have a doubt. Hello, ma'am, am
Yeah,
I
ma'am.
audible?
Tell me, ma'am. Yeah,
Uh,
you're audible, ma'am.
yes, ma'am. In a traditional CNN, what will happen is we'll have number of hidden layers, and each layer,
Hmm.
we will use the ReLU functions or leaky ReLU functions, and
Hmm.
by back propagation, we will come to a point of where it is error free. So now in this quantum computing, where it is using the basic CNN model, so
Hmm.
this traditional approach is applicable even in this quantum, madam? I
No,
don't know.
no. Actually, here, no, ma'am.
Mhm.
So even here in CNN and all, to develop the like hidden layers and all, we have the
Mm.
methods which we are already using, like right. But
Yes,
those
ma'am.
will not be supportive in quantum neural networks. But instead of that, as I told you, to develop the like hidden layers, we have the
Mhm.
parameterized quantum circuits where we are using the rotations and entanglement. So this is a
Okay.
different process again. So ReLU, all those are different. Those will be applicable only to the classical data. So
Yeah,
those
yes,
have
ma'am.
been designed,
Classically.
yeah, designed in that way. So you cannot
Okay.
apply that on quantum. Yeah. So we have different models for that. We have different
Okay.
models.
Okay,
Yeah.
now that computation, as you said, based on the size of the data set, the classical models will take more time. So in
Hmm.
the quantum computers also, if the data set is more larger, even as you said, we have to use GPUs and all. Then how optimized in terms of execution, madam? This quantum computing, how benefit over the traditional approaches?
Yeah, even if the size is too large, let us say a classical system has been taken, let us say some 10 hours for running the
Mm,
data,
mm,
right?
mm. Okay.
For,
Yes.
so in the similar case, if the data size is too large, instead of 10 hours, it will take either 5 hours or 6 hours, but less than that. Time analysis will be different
Okay.
because it will be processed faster, so that you can see that you can even, so even though I'm not saying that the 10 hours can be done only in 10 seconds, it is not like that, but the
Mhm.
10 hours can be reduced to either 5 hours, 6 hours, and based on the GPU, the speed of the GPU, or the which kind of GPU you're using.
Mhm.
But it will be less, ma'am. Time analysis will obviously less, like training and testing, the time taken for that in quantum will be less compared to classical. And accuracy and all, again, you can even observe the accuracy also. If the data set is larger, obviously there is a difference in accuracy. The quantum will give the better accuracy than the classical. But
Yes.
providing that depends on again the parameters what internally you are using, and also depends on the model, like quantum machine learning models. So if you do at model level modifications, then you may get the better results than what you are
Yes.
expecting.
Yes,
Yeah.
ma'am. Yes, ma'am. Thank you. Thank you, ma'am.
Okay. Okay, ma'am.
Good evening, madam.
Good evening, sir.
Madam, is there any automation technique simplification purpose? Any papers are published in this quantum area?
Sir, your voice is not audible, sir. Can you speak louder?
Automation technique, madam. When we are going to apply the
In
quantum,
which
any
which
papers are
technique, sir?
optimization technique.
Sorry, I could not able to hear, sir.
Hello,
Yeah, yeah, sir. Tell me.
madam, to make the optimization simplification,
Optimization techniques, huh?
yeah. Any quantum techniques are applied already. Is there any papers available?
Yeah, there are a lot many papers. As I told you, for optimization algorithms, QA OA is one of the the model, like one of the best model which the most of the people are using now on various applications. So there are a lot many papers, and only in 2025 many papers have been published on optimization models, quantum optimization models. Please go through once. Like we have very good papers in Nature Journal and even IEEE Springer journals. Even transactions also have been published on those concepts.
Thank
Good
Okay,
evening,
sir.
ma'am.
Good evening, ma'am.
Can we apply it for multimodal data as well, ma'am?
Yeah, we can apply, ma'am. We can apply for multimodal data also. But as I
Uh,
told you, the complexity increases when you convert it into quantum. So you need to be, yeah, you need to check how much time it is taking and how, like whether it is giving correct results or not, because you need to convert that multimodal into the quantum, right? So
yes.
only that complex, but apart from that, you can apply it on multimodal data also.
Do we have any existing literature survey on that with respect to multimodal learning?
Yeah, ma'am. I think recently, in the sense, I think 20 days ago, I've seen one review paper which has been published in IEEE Access. I think IEEE Access or IEEE Transaction. I don't remember exactly the journal name. So you just search it with this literature review on multimodal, like quantum machine learning on multimodal. Like you just search it with that particular keyword, you will find the papers. Papers are there, ma'am. But
Sure,
don't
sure.
go with the conference papers or normal journals because those cannot be trustable. Like there
Yes,
won't be
ma'am.
much review happen. So I'll suggest you to go through because a lot of papers have been published in Nature. Like Nature Journal, they have published many papers in this year with respect to quantum machine learning. Once go through those, ma'am.
Sure, ma'am. Thank
Sure.
you.
Thank you. Yeah. Okay, so madam, could you please suggest some projects on QML? Yeah, yeah, obviously, like I'll give some projects on like we will be having one more session on Saturday, not Saturday, yeah, Saturday. I mean, day after tomorrow. So in that we will discuss applications and the projects related to quantum machine learning, and not only quantum machine learning and related to quantum noise mitigation and error correction also. All those will discuss along with the research opportunities and future direction for the faculty who wanted to start their journey in quantum and who are already started, and what will be the like available opportunities for them to apply for the funds and any other like to write a research papers and all. We'll discuss in detail in Saturday's session. That will be completely on the applications, full on applications and projects related to QML and the research opportunities related to the QML, even for the faculty and also for the students. If any students are attending, even I'll show the job opportunities in quantum. Any other doubts?
Good evening, ma'am.
Good evening. Yeah.
Ma'am, can you give the roadmap for the quantum machine learning so that we have the idea about machine learning and deep learning, so that how we can go with which basic concepts onwards in quantum machine learning, taking the reference of machine learning and deep learning applications or
Yeah,
model.
sure. Sure, ma'am. Sure. That only I'm going to discuss on day after tomorrow's session because I'm going to explain. Like we have some applications that represented in the agenda of this particular FDP. But apart from that, I'll also discuss like what are the other opportunities we have, the detailed agenda, like detailed roadmap of quantum machine learning. I'll
Okay,
cover
ma'am.
that.
Thank you.
Yeah.
Thank you.
Yeah. Any other doubts? Okay, if there are no doubts, can we wind up the session? I mean, then you will be having the quiz and assessment questions will be shared with you by the organizers. If you have any doubts in assessment questions or in the quiz, we can have a discussion on that on our next session.
Hello, madam.
Yeah, ma'am. Tell me, ma'am.
Suppose if I want to conduct a seminar like this for students, how can I contact madam to you from the college?
I have my mail ID, ma'am. You can note it down.
Okay.
Okay. If anyone, like even I have my LinkedIn profile. If you are interested, you can even connect me through my LinkedIn profile.
Okay.
So I'm just typing my mail ID here.
Fine. Thank you, madam.
Yeah. So not only for this, if you have any doubts related to the quantum research, or if you wanted to continue, or if you wanted to start your PhD, if you have any queries, you can feel free to reach out to me. It's not a problem.
Okay.
So I just sent my mail ID. It's like mumadiswati@gmail.com.
Okay. The content and the subject you are teaching is very nice, madam. It's easily understandable.
Thank you, ma'am.
Okay, ma'am. Thank you.
Thank you. Yeah. Any other questions?
Ma'am, can you please share your LinkedIn profile also?
Profile. Yeah. One second. One second. Just let me check. So this is my LinkedIn profile. If any of you wanted to connect, you can connect through this. I'm just sharing this. So I just shared my link of LinkedIn profile. Yeah, you can even connect with that.
Thank you, ma'am.
Yeah. So, I mean, don't worry about the quantum machine learning applications and where you can apply it practically. And we'll have a discussion. Like, there are a lot of funding opportunities for you also. Like, as most of you are in academic, like in teaching field or like working as a professors in various engineering colleges, there are various funding notifications have been given by the central government and also by the state governments. We will discuss all those in detail in our next session, like which will be on Saturday. 6 to 8. So in case if you have any doubts in our last three sessions, like we started from 21st, right? So if you have any doubts in these three sessions, that also you can reach out to me on Saturday. We can have a discussion on that also. So even if you have any doubts related to the assignments and also the quizzes, you just let me know. We can have a discussion. Yeah. So any other doubts? If not, can we wind up, organizers?
Yes, ma'am.
Okay, sir. Yeah.